Okay, can everybody see?
Yep.
So, WorldWide Telescope came from a collaboration of many people who happened to come together with ideas that complemented each other in an environment where technology had been growing and the commercial application of the technology had come together and allowed for a whole new class of data visualization, data transformation, and different types of storytelling. And a lot of this came together in Microsoft Research. There was work that Jim Gray and Alex Saleh had done with the Sloan Digital Sky Survey. Curtis Wong was working on an interactive narrative storytelling system that he wanted to use astronomy as a way of showing how that tool could work. I had been working on infinite zoom virtual world type work that had gone on since the late 90s, somewhat interconnected with Jim Gray and Tom Barkley's work in the Terra server. And then there had been groups like the AVM VAMP project who are working to create a more modern way of tagging press release quality images and getting the information and content of these images and defining what spectra they were from, defining how that these images had been collected and processed to be able to take the science quality images that had been collected and explain how they were brought to the public. There were also a lot of visualization tools and techniques and storytelling that was going on through the AstroViz conference. And so that brought a lot of the players together, as well as Curtis, Alex, and I coming to, Jim, Curtis, and I coming together at Microsoft Research and working on a project. So in the history, Jim Gray and Alex Saleh had been working on adding a database layer and a very high performance way of actually querying against all the data that was coming from Sloan Digital Sky Survey. And so Jim had applied himself from, it was a Turing Award winning computer scientist who wanted to apply himself and the work that he did towards astronomy data. In the late 90s, I had worked with the Terra server project to provide some 3D visualization for that. And that sort of, that connection had me also working on the sidelines. And so Jim's work on that project sort of kicked off the work that I would do on the side that would eventually converge with him and Curtis. Curtis, meanwhile, had been working in interactive media of being able to do storytelling through very interactive, all the way back to the CD-ROM days of being able to present a story. And then he wanted to be able to create a tool that would be internet-based, that you would be able to tell stories on, and then be able to explore the data from there. So it would have a storytelling component of a data exploration, and then sort of free-form visualization. And so he had a lot of these concepts, but no code to drive it. Meanwhile, after having been kicked off by Jim and Tom on the Terra server project, I had created a 3D visualization where you could actually fly into the globe and see the globe in 3D with texture map mountains, and it was a pretty cool technology, very addictive to play with. And I tried getting people inside Microsoft excited about it, but at that time they didn't see any commercial value to it, which was kind of interesting given how much Google got out of Google Earth. But so I turned it, the technology I'd created, to explore maps of the moon and Mars, and then decided that I wanted to create a seamless all-sky stitch of the sky in visible wavelength from the DSS plates. I thought I could crank that out in a couple of months, but by the time I got finally it got the seamless version I was looking for, it was about 10 years later, while waiting for Moore's law to catch up. So when we started out at MSR, we had talked about this ideas that we had and gotten together with folks from the AstroViz, people at Harvard, Caltech, NASA, and various different research university planetariums, and talked about these ideas. And Jim Gray and Curtis and I decided to put together a demonstration program for Microsoft Research holds this annual Tech Fest, which is sort of like a science fair inside Microsoft for the projects that we're working on and things that we think might become something of interest in the future. And so we were working on this project, and unfortunately, Jim Gray vanished at sea at that time. And that became the catalyst for Microsoft to take this legendary computer scientist who had done so much for the world and inventing reliable transaction processing, and was one of the instigators of the SQL language and database, and many of the things we hold as important parts of modern computers were Jim contributed to. And now this giant of computer science vanished at sea. And so Microsoft decided to fund turn this demonstration project, which was just a short-term project at the time, into a real fully funded project that would be given away for everyone to use, and from professional researchers to students, and basically do this in Jim's honor as sort of a legacy to him. And so this is where that project that we started got named the WorldWide Telescope after Jim and Alex's paper of the name the WorldWide Telescope. And so we created the project, renamed it in his name, and that started us down to actually defining something that was more than just a demo. Between the time that we launched this and decided that we wanted to build this all-sky viewer, we needed to be able to have the ability to show the entire sky without the singularities. While in the past, when dealing with Earth visualization, using equirectangular maps or Mercator maps were the popular way of representing the Earth, and they created a problem that the poles were not represented well. And so we needed a new way of being able to have a high-resolution all-sky, and in any band that we did or any planet that we wanted to show, we wanted to be able to show pole to pole without these singularities. So we needed to solve that. And I have another slide on that regarding TOAST was our solution to that. We also needed to create a high-resolution all-sky panorama for visible light, as well as all the other bands, because we believed that at that time, people were primarily dealing with small segments of a single band as an image, and maybe they would bring in a few related bands together for specifically showing some data on an image. But the idea of having the whole sky in multiple, across the whole spectrum, right, from radio all the way to gamma rays, that was just not something anyone could even envision as a possibility or decide how this could be done. So the data, some of the data was there and collected, but it needed to be transformed into these tiled panoramas using this new TOAST projection that we had. We also needed to build an authoring and playback environment for the storytelling and doing this in Scratch, something like building, something on the complexity of Adobe Premiere or, After Effects, except for tuned for astronomy. We also had to find standard ways of exchanging data, and also ingesting all this data to make it easy for people from different organizations to be able to put their data in WorldWide Telescope. We knew that to start with, we would have to curate all this data to begin with in order to jumpstart the project and make it possible people to use the storytelling engine and to see what the concept was. But we knew that that was not a tractable solution for the long term, because we eventually needed people to be able to create their data self-service and have all their projects just publish their data in a way that would be usable and visible through our browser. So the idea was WorldWide Telescope would be like a web browser for astronomy data. So some of the problems that we had to attack in order to do this was getting this all sky imagery. One of the things that we wanted to make sure is that we had an intermediate format that would allow us to deliver pixels from the cloud onto people's clients efficiently in 3D. The equirectangular projection, which was what other companies who were doing GIS and things like that were either picking Mercator, which couldn't represent the poles at all, or equirectangular, which had an explosion of data. So a single strip of data, a single pixel at the pole took the same amount of storage as the entire equator all the way around the Earth did at that same resolution. So that meant that if you were trying to create a tiled multi-resolution, if you went anywhere near the poles and you try to zoom in on it, there's no computer on Earth that could have enough memory to actually load it all at once. And so we needed to solve that, and Toast was the solution. It allowed us to be able to represent. We start out here with this octahedron that becomes, in 3 dimensions, becomes subdivided until it approximates a sphere. It's subdivided and normalized. And then each of those triangular faces is mapped to this triangular face of a warp of the all sky or an Earth image or planetary image. That's all the pixels are fit into this space. And this starts out as a rectangular that's subdivided over and over again, so that the tiles, as you zoom in, represent a local area. So you never have to download more than a handful of tiles to be able to look at any point on that on the Earth or any point in the sky. And so this allowed us a way of being able to look, and there was no favored spot. The poles weren't any different than any other point on the sphere. So we solved many of these problems. We cooperated with people like the Space Telescope Science Institute and Caltech, Harvard, et cetera, to be able to help with this idea of launching this platform with all the data available. And we decided that this was something that was very cool and that people would really love. The world loves the astronomy pictures that Hubble brought us and things like that. So we thought that this would make a big splash for Microsoft as well as for our partners. And so we showed this to TED, and they asked us to basically announce WorldWide Telescope in a TED Talk. And so that's where we first launched WorldWide Telescope and announced it to the world. And we were invited several times back to show the progress of WorldWide Telescope as we adapted new features, including virtual reality and various other features as time progressed. There were regular updates that Microsoft produced for many years after that, and the functionality grew. So some of the things that we went into is first, from just the storytelling, we added support for things like the VO protocols, interoperability with SAMPs and VO tables, and being able to send data back and forth between different VO applications. We added support for full dome planetariums to be able to do entire planetarium shows and domes from a single laptop with a fisheye projector all the way to Adler Planetarium at one time had 42 computers that would run together running Worldwide Telescope across their projector systems. We supported things like kiosk displays and other animations for like museums so that people could easily author a story or an interactive exhibit and then be able to play that on a touchscreen computer that then they could integrate as part of a museum piece. We also, early on, this was a Windows only that required a very expensive cutting edge machine when we first launched. But by the time web technologies had improved, we figured out a way to be able to take all the code from Worldwide Telescope and transpile it so that it would run inside a web browser with a lot of work that we did to be we create a web version of this. So at this point, a lot of the ideas that we had at Microsoft Research, this project had really kind of opened up a lot of new areas for research, as well as being able to provide this tool for astronomy. But the reorganization at the company, it became time to transition to a more permanent home that could deal with it as a product for astronomy rather than just being a research vehicle. We had had millions of people download and use the product. We had millions of people seeing Worldwide Telescope running in museums and planetariums. But this wasn't something that, there was not a profit center for Microsoft. And while it was a great gift to be able to remember Jim Gray by, we realized that in order for it to succeed on the long term, it needed to be an open source and it needed to have a home in astronomy. And that it would be free of the whims of budgets of enterprise companies that, don't really have astronomy research as the principal, aim for the company. As leaders came and went, we wanted Worldwide Telescope to be able to survive and have a good home. So we went ahead and talked with a few different organizations and eventually decided that .NET Foundation was a good place for the open source management of owning the patents and the code, and that the AAS would be given the project management and the development role and continuing to develop Worldwide Telescope and promoting it. And eventually at the AAS, Peter Williams became the director of that effort. And I'm going to hand it off to Peter for him to continue the talk on where Worldwide Telescope is now and where it's going in the future.
Great, thanks, Jonathan. All right, let me share my screen here. Hopefully you can see a title slide. Yeah, so Jonathan gave you some of the background, and yeah, I'll take it up with the present and the future of where things have gone since that handover. So yes, the American Astronomical Society is the major organization of professional astronomers in North America. And the mission statement of the AAS is to enhance and share humanity's scientific understanding of the universe as a diverse and inclusive astronomical community. And I think, this is a perfect fit for Worldwide Telescope. And I think people recognized that back then. And that's why it was a really, inspired choice to find AAS as a home for Worldwide Telescope. The way I think about it is, what I like to say is, Worldwide Telescope, it's a tool for showcasing astronomical data and knowledge. And one of the key things there is, not just data in terms of pretty pictures, but knowledge, the storytelling capability that Jonathan talked about of sharing, using those data to help people understand the science of astronomy. And there's just, a million different things that that Worldwide Telescope can contribute to the third things that the AAS cares about. But that being said, the AAS is primarily an organization for professional astronomers doing research. And so what we've been emphasizing has been that side of things, and specifically the web version that Jonathan mentioned. Just a lot of astronomy researchers in the US, they're not even running Windows. So the Windows app has that limitation. And the choice to develop that web version back, and I think since 2009, was incredibly inspired because, the web was pretty young back then, but nowadays, web browsers empower you to build fancy interactive multimedia applications like Worldwide Telescope, and you can just deliver them. They can run on my phone. They can run in the dashboard of your Tesla car. It allows you to increase the reach of Worldwide Telescope so far. And it also works well for researchers in particular. So this translation to the web is difficult. So this little graphic that I have here is kind of a schematic from the automated processing that happens whenever we update our code online. And this is just sort of to convey that we have the sort of sequence of steps that run, because whenever you're building a web application, you have a lot of interlocking parts. As Jonathan mentioned, the first step in what we do is taking the original C# code and translating it to JavaScript. And then we have to do a bunch of tests and deployments whenever something's ready to deploy. So it's a lot of work to make that leap. But the motivations make it all worthwhile. And certainly, we couldn't have done it without all the work that was done, over the past decade. But since that work has been done, it really just opens up a whole new avenue of what we can do with Worldwide Telescope. And particularly for the research side of things, we've seen that there's this really nice fit together where for astronomy research these days, more and more scientists are using Jupiter to explore data. And in astronomy especially, we have this concept of a science platform where you don't run code on your own computer anymore because the data sets are just too big and the processing power that you need is too large. And so projects like the Rubin Observatory, major observatories across the world are all building this idea of you'll log into a science platform through your web browser and you'll run code through there. You'll visualize your data through there. You have to do everything through the web browser because that's how we connect to remote computers these days. The challenge one of the challenges that comes with science platforms is that a lot of our scientific tools for looking at data are not web applications. They're traditional desktop applications like DS9, and they're really good for what they do, but they're not very compatible with this idea of I connect to some cluster in the cloud through my browser. But this web version of Worldwide Telescope is a perfect fit for that. And it can do a lot of things that existing applications just can't. So I wanted to start by showing off a little bit of that, but I figured I would actually I'm going to go over a few screens here, show off. So this is our web client, which is a pretty close approximation of the Windows client of Worldwide Telescope. And so this has been sort of the historical Worldwide Telescope interface, where we have this, what is now a very classic pan and zoom interface. And I should mention that over Zoom, this probably looks pretty jerky and doesn't look that good. But on your own computer, it can be incredibly smooth. Web browsers can use your graphics accelerator cards now. They're incredibly powerful software deployment platforms. And so, we have this really beautiful, slick, smooth interface. But unfortunately, it won't look that way to you. So this is sort of the all-in-one interface, which if you go to the worldwidetelescope.org website, by default, it will bring you to this. But for what we can do now is a little bit more sophisticated interface that interacts with the Jupyter environment. So what I've got here is a screen from the Jupyter Lab application. I just want to show very quickly the sort of thing that you can do where we've built a Jupyter Lab application where I can pop open the Worldwide Telescope viewer as a window inside this application. I can split my screen like this. And here we've built kind of a custom application that takes into account the fact that, we can do things now like run Python code over here. I'll pop something open, and WorldWide Telescope over here. And I think there's just a ton of opportunity to kind of explore this interface between interactive coding with this powerful visualization tool at the same time. And so, we've thought about this as something that's aimed at researchers, where say I use a major telescope, there's data downloaded, I can download those data and I can pop them open and visualize. So right now, this data set that I'm loading lives off in the cloud somewhere on some server that I don't even know about. But I can look at the data. And this particular file is pretty small, but we have demos where you can download, we have a 25 gigabyte data set of Andromeda Galaxy, hundreds of hours on the Hubble Space Telescope, where you can explore the data interactively without having to download into your own computer. And I'll show, you can do things like change the color map of this particular FITS file, and I can change the cutoffs so I can explore some of the fainter structure or things like that. So this is the kind of thing where this web version of WorldWide Telescope started out just as kind of, let's copy the Windows application, but because it was engineered in a very forward-looking way, we can do all these exciting new things with it. And one thing that I think would be really exciting that we just haven't really had the resources to pursue is thinking about this for education of, so often when students are learning how to code, you learn a little bit about programming, but you run into this barrier of, how do I write a program that does something interesting? I can print out Fibonacci numbers or whatever it might be, but you sort of quickly need something to actually do with the code that you're writing. And the ability to, from here, I can write Python code that controls what's going on here, I think just opens up a ton of opportunities for ways that you can, learn how to code, learn how technology works, learn about astronomy all at the same time. And I hope that we will be seeing more of that in the future. It's just a matter of there's a million directions you could go, and this is one that we don't really have the resources to do ourselves at the AAS. Besides that, another thing that I wanted to show was another usage of the WorldWide Telescope as sort of a piece of a web application, which, one of the reasons that web technology is so powerful is they let you mash together different pieces like this. So this is an educational web app put together by people here at Harvard, which helps you, this particular thing is educating about the Hubble law and the expansion of the universe. And this is a nice little application where if I can click on here, it will take me to different images of galaxies, and it will pull up information about them. And what you end up doing is you use this tool to measure the sizes of galaxies, and we have a guess of how far away they are, and we learn about Hubble's law of the expansion of the universe. But the thing that I think is really cool is this app was put together by a couple of people who are not professional programmers. They're astronomers and educators, and you don't have to get a whole degree in computer science in order to be able to create an app that has some nice interactions and also looks really good and helps you sort of realize a vision of a way to help students learn through interactive educational work. And this is the kind of thing where, again, the power of this sort of web-based version is, this part is the hard part. Everything that Jonathan did, the brilliant toast format, all the work to make this really efficient and fast and smooth, that you need some really, profound software engineering to make happen. But creating this kind of thing where you can help students look at different galaxies and measure them and do a basic Hubble law experiment is something that, you can do with some sort of web skills that a person like an educator will have. And so I'm really excited about the ability of the WorldWide Telescope on the web to open up this kind of functionality more broadly. So they've created a few such applications, and there's just a whole world of them that you could create instead, or even beyond that. Another thing that we've really been working on at the AAS is tools to help the WWT app. So as Jonathan alluded to, getting data in there is a very important part of it. And I think it really is important to say that, the engine that does all the rendering is really brilliant engineering. It works incredibly reliably. And the difference between something that works 99% of the time and something that works 99.99999% of the time can be really hard to achieve. And WWT does that. But equally inspired is the way that WWT interacts with data. So it's a very open data model where people will ask me, how do I get my data into WorldWide Telescope? And the answer is, I mean, you can do it. You have to know what to do, but it's designed from the ground up to be very extensible to allow you to get your own data in there. And even the Windows application back then, you can load in data sets from all over the internet and get everything right there. And we've tried to sort of build on that very open-ended model as it is. So a lot of that involves that we've been working on some software tools. So we have Python code, a package called Toasty, which does that kind of toast processing using that spherical projection that Jonathan mentioned, because the math behind it can be a little bit tricky. And so that's the kind of thing where it's really helpful to provide a tool that helps people work with that. We've developed a tool called the Aligner, which helps with this problem of sometimes you have a pretty image, like this little picture of a galaxy, and you don't have that AVM information about specific coordinates on the sky, and we want it to show up in WorldWide Telescope. But we might have the underlying data that this image is derived from. And so sometimes you can use a service called astrometry.net, where if you haven't seen it or you tried it, astrometry.net is amazing. You can upload it, if you take a picture of the sky using a basic sort of personal type telescope, astrometry.net with very high reliability will be able to figure out exactly where it is on the sky just by matching star positions. And the Aligner sort of builds on the same ideas, but is tuned for, say, if you have a Hubble image, the star positions are not, astrometry.net won't know about the stars because it's just so high resolution. So we need to use similar techniques. Part of this whole data ecosystem is that you need to provide a lot of tools. So for instance, to preview this stuff with the web-based version of WorldWide Telescope, you needed to run a little web server on your computer. And so we have tools that do that kind of work to make it easy to double check that your data sets work. And then another one that certainly is important to mention is there's the HIPS data format, which is kind of comparable to Toast. Frankly, Toast is technically superior, but HIPS is used by a lot of people. And so the China VO group did a really great service by developing support for this and then contributing it to the open source project. And so we've integrated that into the AAS Windows application and the AAS web engine. And so that allows us to visualize a whole new raft of data sets. I think our latest update was something like 800 new data sets that we get thanks to the support. And then I think a bigger point that I want to make here is that a complicated application like WorldWide Telescope is not just the rendering engine that does all that great stuff. You have to deliver really a whole ecosystem, the tools to give the data, the documentation. It's a really incredibly huge effort to build everything that you need to do, but you really need all those pieces in order for the thing to work. And I think this work has paid off well. So we're working on the next Windows release, and I just did some updates of our data sets. And thanks to these kinds of tools and things like the HIP support, we're going to more than double the number of images that are kind of built into our standard data sets. So the number that I have right now is 4,533 images, from all sky surveys to sort of individual PR images that people have published. So talking about the future, very soon we'll be announcing or launching something that we like to call WWT 2022. And so the idea here is that, like, if you go to our WWT GitHub organization where everything is open source, we have something like 50 different repositories. We've got a ton of packages, which again is part of, the full ecosystem has to be made out of a lot of packages. We're always making little releases. We found that it's really, really valuable in terms of managing a software project to put yourself in a position to release frequently and and automate those releases so that you can really do it easily just to fix a bug and also to sort of keep things, the easier it is to release, you don't get into this issue where you have a whole bunch of work piled up, and it's sort of a really big jump to actually formally get it out there. But the downside of all that is that we don't really have, we've done a lot of work over the past several years, but it's, there's an important new feature that was launched in this particular Python package in version 0.14. It's hard to sort of really take in all the progress that's being made. And so we want to talk about WWT 2022 as, it's not a new piece of software. It's just giving a name for all the stuff that we've been doing over the past few years and really giving us a way to celebrate the whole new list of features. So the support for HIPS, the Jupyter applications, the Aligner project, the data tools, all these things, they're out here now, but very soon we'll be having a formal launch of the 2022 edition with some documentation that ties it all up and really, gives us a way to say, this is what WWT has become. And we certainly envision next year putting out a WWT 2023. So I think a lot of the work that we've been doing, there's a lot of great new features, and they really provide us a foundation for going even farther in the future. So there's some things that are just kind of always things that you do. So importing new data sets, whatever the new releases are, both in terms of press releases and scientific data releases. There's basically at least once a month, there's something exciting and new that we'd like to make sure that it's available in WorldWide Telescope. The new Jupyter Lab app is honestly, it's pretty new, so it can do some good stuff, and it's got the important stuff from the WorldWide Telescope engine, but it still needs a lot of features to help people get their work done, either as researchers or as people who are just in that environment exploring astronomy data. Likewise, all these supporting tools are really important. And, what we find is someone puts out a really cool new all-sky map that we want to include in WorldWide Telescope. And it turns out that it uses a new image format. And so we need to go and add the support to make that possible and try and make things easier. One thing that I'd really like to do a lot more of is improve our documentation. We have a lot of documentation, but honestly, we could do better in terms of tutorials and sort of useful guides for people trying to accomplish certain things and linking it all together. I'll provide a link to our docs website in case you're interested, but there's just an enormous amount out there, but it can honestly be too much and a little overwhelming. And I think we need to do a better job of giving some nice entry points for people who are trying to use the system. And of course, there's always fixing bugs and making sure that things keep working. And once again, when you're really focusing on a web application, there's things in the web where some library that you use has an issue and you need to upgrade it, and that ends up being a whole bunch of work just to sort of keep things running. Or where we're using Microsoft's Azure cloud services to power all of WorldWide Telescope's web servers, and those cloud services are always evolving. And so there's just a lot that is sort of stuff that you need to do to keep the software in good running shape. A bigger picture thing that has been on my mind recently is that we now have gotten so many data sets in the WorldWide Telescope core corpus that the standard application has a folder-based explorer where you can click on different categories of things and explore different images. And frankly, when you have thousands and thousands of images to choose from, that folder interface doesn't work so well. And I'm really interested to think about whether we can build, a different interface that will help people discover astronomy data. And it's probably actually not one interface, but multiple interfaces. The way that you're trying to find data if you're a professional astronomer is very different than the way that you're trying to find data if you're just, a person who loves astronomy and is looking to see what the latest cool science thing is. So hopefully we'll get a chance to explore a range of different ways to really get all that data that's in WorldWide Telescope now out to people in sort of the ways that, I really want people to be delighted by discovering some image or data set or tour that they didn't even think they wanted, and they'll discover it and realize that it's exactly what they needed. So that's kind of one of the really the bigger things that I hope that we'll be able to tackle this year. So just to try and summarize a few things. So some of the takeaway points that I wanted to put down. So software architecture matters. I really think that one of the things that has enabled WWT to succeed has been, there are some core pieces of technology, especially the rendering engine and the design of the data model that are really forward-looking and, have held up extremely well. And, you can work around flawed foundations, but it really makes your life a lot better if those foundations are solid. And I think that a lot of the reason that WorldWide Telescope is still doing well is because those foundations are in fact extremely well done. I've found that, a lot of really famous, successful pieces of software, getting to my second point, there's always a big ecosystem around them, and you need to have that ecosystem, but they're often built on a few very important insights that set them apart from the rest. But yeah, that ecosystem is very important. And then the last point I wanted to have is we probably all understand this more now than people did in the past. But the web is really, if you want to create an interactive multimedia application in the year 2022, the web is really the place to start. There are things that are always going to require desktop computers and high-end graphics. Things like powering a planetarium is not things you can do on a web browser. But web browsers can do an amazing amount of stuff right now. And the way that sort of transforms our ability to roll out application updates, feed people new data as whatever the latest image off of Hubble literally today is, it really transforms how we approach all kinds of software, but especially things like WorldWide Telescope, visualization software, data exploration software. And as scientists, we're often very limited in the resources that we have to build these kind of tools. But fortunately, companies like Microsoft are spending billions of dollars literally on building out this kind of web ecosystem and allowing us to build rich interactive applications there. So I think there's just a huge opportunity for scientists to ride that wave. Finally, I have a few links. So this first one will open up that Jupiter Lab demo, and you can play around yourself. I also have our GitHub organization and our documentation website, and also a short link to sign up for our newsletter, which we send out sort of a monthly update. And soon we'll have an update about the WWT 2022 release. So thank you for attention. Really excited to be able to talk to you about WorldWide Telescope, and really glad that we could, both Jonathan and I could give two halves of the story. And I'll stop sharing, and I guess, is it time for questions?